Okay, so what we just saw, this formula that some of you guys didn't get written down yesterday, S sub n right here technically means the nth partial sum. Technically means the sum of the first n terms. But infinite means there is no end. It keeps on going. Dot, dot, dot is included. So the best way to write this would be, oh, now I can't get back to it, can I? Struggle. The best way to include this is to go ahead and erase the n and say, okay, it's not a partial sum. It is the sum. It is the entire sum. Did you guys erase your little n? Erase the little n. The way that we'll keep these separate for a geometric series, there is an S sub n formula, true? It was back here on this page. There is an S sub n formula for the nth partial sum, dun, 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 right? However, did you guys notice? Look at what you just wrote down and look at what's on the board. What's different? They're really, really similar, but what's different? This has somehow disappeared. The question is why? That has somehow disappeared. The question is why? There is no ending, but there's still a common ratio, isn't there? There's an R in this formula, right? There's still a common ratio. There's still an R in that formula. But let's go back to what we talked about at the very end of yesterday, about when this infinite sum will exist and when the infinite sum won't exist. It won't exist. The series is divergent when R is bigger than 1, less than -1, or equal to either. But the sum will exist if R is less than 1, greater than -1. And we saw examples of that yesterday. So why did the little r to the n disappear and what is going on? The reason is, I'm going to show you just a quick little heads up, and it's in preparing for chapter 12. What chapter are we in right now? 10. I'm preparing you for chapter 12, and the answer is yes. You're welcome. Oh, we're not even in chapter 9. We're in chapter, sorry, we're not in 10. We're in 9. Either way, I'm still preparing you for chapter 12. Yep, because we're skipping a chapter. Skipping chapter 11. Okay, ready? Why does r to the n disappear? This is why. There's a spiffy mathematical notation called LIM, and some of you might have seen your friends that are in calculus, maybe at some point, writing LIM. What it means is the limit. What it means is the limit. The limit as n goes to infinity. Wait, who's going to infinity? Oh, because n is telling us where to stop, right? And what am I telling to the stopping place? You guys are used to the arrow. That means approaches from earlier this year, right? The limit, I'm asking for what is the boundary as n approaches infinity, as the end keeps on going to infinity. And who am I trying to find the infinite, or who am I trying to approach infinity of? S sub n. This formula comes from taking the S sub n formula and approaching, or having the n approach infinity. Now, does anybody know how we can have n approach infinity? Any ideas?
R is greater than 1.
Well, we could do it for r greater than 1, and we could do it for r in between 1 and -1. Grab out your graphing calculators. We're going to approach infinity today, guys. You ready? Grab out your calculators. I'm going to give you a couple cases in order to practice, and they're actually going to be the ones from yesterday. If you don't have your calculator, just kind of peek on with someone near you. Is that the question? Awesome. Greater than 1 or less than -1. So the magnitude of the number, it has to, like if it's -4/3, the magnitude is just the 4/3 part, not the negative, and that's bigger than 1. Does that make sense? So that would be divergent, or if r was 9/2, the magnitude is greater than 1, divergent. If r was -1.1, that's greater than 1. Okay. If you guys were to go ahead and put in, and we can just put in the function, we don't have to put it in somewhere else. Let's make up a series. Let's have the first term be 3. Let's do our little alpha. Actually, let's put it in a parenthesis just to make it nice and pretty. Parenthesis. Alpha y equals, let's put in a nice little fraction. Give me an r of a divergent series. Any r. Ready, set, go.
14.
14, sounds good. 1 minus r, 14 to the power of, and then put in a variable, x. Because we're not ending it, we're trying to think about what happens when the n, or when the little power, gets bigger and bigger.
I can't do the fraction thing.
You can't? You did alpha y equals?
His stats are on bottom.
Oh, is your poor little calculator not as up to date as it could be? Oh, that's so sad.
Yeah, inequalities. That doesn't work with inequalities on.
Does anybody's work when you try to put, wait, some of you guys have the inequals on. Is that what you guys are saying?
Yeah.
Turn that off and you'd be okay?
Oh.
You're right.
Oh.
It's trying to be technical.
Yeah.
There you go. That makes sense. Because the alpha buttons are being used for the inequals. Okay, now we have it. We're okay?
No.
I plugged in the formula for S sub n for a series with an initial term a sub 1 of 3 and an r of 14, because Caleb said so, and it's a divergent one. What happens with a divergent series when we try to, for the S sub n formula, have x get, ooh, yuck. I don't like the automatically generated one. That's yucky. Can we change that? Do you remember Graphing Calculator Handbook? How do we change the automatically generated table?
What's the plus?
You can't hit plus to change just the change in table, to go by like 5s instead, which is kind of snazzy. You guys see the trick? That's kind of cool. You can change and go by 10s instead, but I don't even want to go by 5s or 10s. I want to plug in my own numbers. Good. Second window, table setup. Just change all that beginning and change in thing and just say ask. I want to do it myself. There we go. If you guys have numbers in there when you do ask, just hit delete, delete, delete. Make it all nice and clear. How can we approach infinity? Starting from, let's start from 1, if r is 1. Well, that's not very exciting. If r is 1, it's just a sub 1. How do we approach infinity from 1? One step at a time. Give me a step. What's a step towards infinity?
2.
Okay, you're going really slow.
1.5.
Even slower. Go towards infinity.
1,300,000.
Okay, that's a little fast. Something in between.
20,000.
100, all right.
Not sure.
You went from like 1.5 to
I got
a million.
1 to 5 to 1.3.
Ah, stink. I wonder why it says error. Does that mean it doesn't exist? Okay, maybe we just went too fast. We'll do the 2. And then let's do the 2 squared. Then let's do the 4 squared. Then let's do the, whoa.
Oh, because it's
Woo! What's going on?
you're getting big numbers.
It's getting huge. Times 10 to the 17th, kiddos. What does that mean? What's that 17 indicate?
17 zeros after.
Go 17 places.
5, 0, 0, 0, 0,
Woo!
0, 0, 0, 0.
So wait, the first partial sum, the second partial sum, the sum of the first 4, and the sum of the first 16. This thing is really big because what was our common ratio? 14. Do you guys, can you see what, this is the S sub n formula. Can you see what the sum is doing?
It's like getting bigger.
It's going to infinity. It's divergent. The sum isn't getting closer and closer and closer to any answer.
Should have gone to a
Now, yeah, maybe it's just because the 14 was so big. So let's go ahead and change the 14 to be a smaller one, but still of a divergent.
13.
3.2? 3? I don't care, either one.
2, 3,
4.
All right, we'll do 3.
and then put in a
Hold
million.
on. I don't know why there's a random space. Oh, that's all better. Second window. And you change it to ask if you guys weren't able to figure it out. Okay, so go to our second. Still pretty big though. Do you think it's still going to infinity?
Yeah.
Do you guys realize that the error is just because this is getting too big? If I was to go to like 50, there's only so much scientific notation it can show. If I was to go to 75, still pretty good. If I was to go to 100, if I was to go to 200,
That would be too big.
as soon as this E gets too high,
No, that was
still alright. How high did you guys, oh, 300? Okay.
300.
No.
300 is there.
300 is
200 is
Too big.
Try 200 is too big, I think.
215.
Oh yeah, let's try 201. Yeah.
But either way, guys, hold on.
No, 201, 201.
2 and 5 is also.
It's really cool that you guys are trying to find like the place where it first starts to fail because it's so big. But here's the long story short. What's it doing that's making you have
It's a
this
big
whole
number.
process?
209 is the highest.
Yeah.
2 times word.
Yes,
Yeah, 209.
What's the
Good job,
decimal
let's go
point?
D.
No, find decimals. Find decimals.
Okay. So long story short, it's still getting bigger and bigger and bigger and bigger.
But it's
It's diverging. So what makes a converging sequence? Here's a long story short. If you plug in an R, in the divergent category, so greater than 1 or less than negative 1, as you raise R, look, to approach infinity, you just take steps to get there. Plug in 5, plug in 10, plug in, that's all this means. It means just make N get bigger and bigger. And as N gets bigger and bigger, what happens to R? It gets bigger and bigger. And if you plug in bigger and bigger R's, what does that do to the S of N? It gets bigger and bigger. So what's so different about this formula working sometimes? Give me a convergent ratio.
It'd be like 45.
Sure. Will it still fit? 0.5. And then let's do 0.5. Now pause. Before you go to your table, I know some of you are like, yay, I'm going to go look. Pause. What happens if we just raise? Look, the x is only in this spot. So when we plug in 5 and 10 and 50, we're plugging it in here, and it's happening to the 0.5, and then we're solving the rest.
So you become 1/4.
Yeah, if you have 1/2 or 0.5, what's 1/2 to the power of 1? 1/2. What's 1/2 to the power of 2?
1/4.
What's 1/2 to the power of 3?
1/8.
What's happening to the r's in the formula?
Shrinking.
They're shrinking. So if I was to raise 1/2 to smaller and smaller, bigger and bigger and bigger powers, the number gets smaller and smaller and smaller and smaller. And guess what? Hold on, I'm going to show you a really mathematical trick. If R, absolute value is less than 1, that's a little trick that it's in between 1 and negative 1. The magnitudes are smaller than 1. This term is going to approach 0 as you have n expanding. If it's 1/2, like our example, 1/2 to the 1 to the 2 to the 10 to the 50, that thing's getting tiny, 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 like 0.0000000. This is approaching 0. If it's approaching 0, a limit is a mathematical tool that says, hey, as n increases, think about what's happening. As n increases, little baby r's raised to higher powers get smaller and smaller. So we can say, in essence, what's going to happen at infinity that we can't get to, but we can approach. What's going to happen at infinity? Take that out and just keep the rest. A limit says, look at what's happening, where it's approaching, and then just go ahead and say, oh, cool, so at infinity, that's 0. But you can't get to infinity. No, but you can think about the boundary, and as it gets closer and closer and closer to the boundary, you can say eventually you're arbitrarily close, snazzy math terms. Infinitesimally close, you just go ahead and make the conclusion, let's just set that equal to 0. Now, hold on, pause. Before I go to the table, don't you tell me what you've heard or what you've seen if you've already gone to your table. As we go to infinity, what value should this series, which is 3 plus 3/2 plus 3/4 equal? Don't tell me. You would plug into the formula. You would say the limit as n goes to infinity, technically, of the S of n formula, which would say 1 minus 1/2 to the n, all over 1 minus 1/2. Calculus would say, sweet, this guy is going to go to 0. And then we would solve and say, okay, the infinite sum would be 3 times 1 over 1 minus 1/2 is 1/2, aka 3 times the reciprocal of 1/2, which is 2. What do you guys see as you go to your table?
Anything after 16 is 6.
Now, careful. After 16?
Yeah. After 16. 16 is less than this.
It's not 6.
Roasted.
Wait, it's
It's rounded to 6 because it can only show so many digits, but what is it actually? 5 point, no, I lost count.
8-6.
9, 8, 6, there you go. How about 50? Is it actually at 6? Now, hold on. Guys, do you see how if it runs out this many digits, it has to round? Right? So what happens if it runs out of this many digits? Oh, it rounds. But the question is it actually? No. Because if we were to go a little bit above 32, let's say we were to go to like, what, 35? Maybe?
No, that's
It's still 6.
I think it's still gonna show 6.
Nope, it's 5.83.
It's getting smaller.
If we were to keep going to 38. I'm not going very fast, but that's okay. 5.98.
Just about.
Do you see what's happening?
Stupid.
Is it ever hitting 6? And the answer is no. But is it? Basically, for forever, going to be getting closer and closer to 6. Yes. And so what do we say? At infinity, you can't get to, but you can approach, but you can be at. At infinity, what is the sum?
6.
6. 6 encapsulates the infinite series.
That's stupid.
All right. All that to say.
Do all convergent series have a point where like it reaches infinity even though it doesn't actually reach it?
All convergent series, we say their infinite sum, which this formula will solve for, but only with convergent series. The sum encapsulates the infinite addition. Does that make sense? All right, cool kids. Sorry, all I have to say. It's a really cool idea. It really leads into calculus, and that's why I kind of took some time on it. When we get to chapter 12 and I say, hey, this thing called limits, you're like, oh, we've seen that once, I think.
Wait.
But can I give you one other quick illustration, just a fast one? This one illustrates it a little bit better as to why this happens. Dude called Zeno. I don't know if it's spelled with an X or with a Z. I always forget. Zeno's paradox. I feel like it's an X. Anyway, Zeno's paradox says, you guys know in like different fields we can say like an arbitrary unit, right? Let's say there's one arbitrary unit between me and the stool. Cool? Zeno's paradox says, the steps I take towards the stool, I'm supposed to cover half the distance every time. Are you sure?
Get close.
So, I'm going to cover 1/2 the distance. So, this is one arbitrary unit. How much distance have I gone in this one step if I did it exactly correctly? We'll say half. Okay? How much distance did I cover? 1/2 of the arbitrary unit. Cool. How much distance have I covered now?
Another
1/2 plus, half of a half is a fourth. So 1/2 plus 1/4. How much would I add to the distance now?
1/8.
1/2 plus 1/4 plus 1/8. How about now? 1/2 plus 1/4 plus 1/8 plus 1/16. This is a geometric series. My common ratio is what? 1/2. What if I was to go again? Plus 1 over 32, right? Plus 1 over, I keep going. 1 over 64. Now, the question is, will I ever get to the stool? That's the paradox.
No.
And in the theory of it all, if you could do it perfectly, and if my toes were infinitesimally thin, I would never get to the stool, right? But the question is, what is my distance still converging to? The stool. What is it bounded by? The stool. But isn't it an infinite addition? 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64 plus 1. So infinitely many steps to get to a finite distance. So 1 would be encapsulating the infinite steps. Does that make sense? But you can't ever get there. But eventually, aren't you basically there? That's the idea. Well, that's the question. That's why it's called a paradox. Okay. Anyway, sorry. I had to do that one. I had to do Zeno's paradox before we leave this
Depends
thing.
on how you think of
Question. How do we apply all this blah, 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 which is really cool and actually pretty deep. If you want to think about it, most of my artwork up there somehow illustrates this idea. of up there. MC Escher, super geometric. Oh, actually, those are fractals. That's a reflection. That's a little different. But it shows fractals in the leaf. Anyway, sorry, some of them are fractals. But other ones? Little baby fishes. But they're getting smaller and smaller and smaller. And as they get smaller and smaller and smaller, how many more fishes are we fitting in?
A lot more fishes.
More fishes. And as they get smaller and smaller and smaller, fitting in more and more and more and more, the limit as n goes to infinity of fishes is still converging to that circular region. Come back. How do we use all these really philosophical ideas? Kind of, they really are. Monks actually debated as to whether or not calculus should be allowed because of the hard idea of infinitesimals. But coming back, how do we use it to solve the problem that we're given?
Plug it into your calculator.
You can't plug in infinity. Good try. Can you approach and kind of cheat and say I'll plug in 5 and then 10, then 100, then 1,000? Sure.
Wait a second.
But what if there was a formula that encapsulates that whole going to infinity process? And there is. Limit as n goes to infinity of, question, what do we know from this sigma? Who's a sub 1? No, we plug in 0. Anything to 0 is 1, 1 times 4 is 4. What's my common ratio? Yeah. Because then if you were to go to 1, then suddenly there's a 0.2, go to 2, there's another 0.2, there's another 0.2, so we have 0.2. Another way of saying it is 1/5. If I was to take the limit as n approaches infinity of a sub 1 4 times 1 minus 1/5 to the n all over 1 minus 1/5. We just talked about what happens to this little 1/5 to the n thing. It's getting tinier and tinier and tinier, and so we say you converge to 0. So we're using 0 instead of you because we're going to infinity. The other way of doing it is to say, hey, you know what? This R is of a convergent series. Then I can use my nifty formula that just says A1 times 1 over 1 minus R. So you can memorize the formula and say, it fits, good. Or you can plug into S sub n and say, I can do a little bitty calculus. And either way. This is a by hand problem, kiddos. This isn't a calculator problem because should you be able to do 1 minus a fifth? And the answer is, hopefully. Isn't that 4/5? And isn't 1 over the same thing as the reciprocal? And what do we end up with our final answer? The infinite sum will be converging to 5. Question, how about number 80? Some of you might have gotten stuck on these ones. We're going over a couple of questions. We'll grade 9.5 tomorrow. We'll start 9.3 tomorrow. We'll just start 9.5 at the end of class.
Did you grade 9 too?
No, I'm grading 9 tomorrow.
That's not my question.
Whenever I pull up the answer key, we'll just go back to where we graded it.
Well,
I thought we did.
well,
Yeah. We'll find the video. Okay, question. Does this infinite sum exist? Yes or no?
Wait, no.
It's a negative number, that's all.
Ew, guys. Yeah, it is a negative number. It goes back and forth. How do we find common ratios if they...
Put them over each other.
Can't we just do this? I don't want to do these ones. Those look gross. Those ones look nice. Let's just divide those two. Now, if you don't believe whether or not it's true, you need to double check it and say, oh, okay, 25 over 6 all over negative. Have fun with that one.
You guys can just multiply.
But can't you just multiply by the reciprocal?
good job, Jason.
Next one.
Okay, those just end up being the same thing. 1 and 5 and 1 and 6. Okay, we have our common ratio. Question, what is the infinite sum?
6 over 5. Negative 6 over 5.
It doesn't go to a single
Infinity is.
It's actually not going to be infinity, it's actually going to be DNE because it's going to go bigger and bigger positive and then every other bigger and bigger negative. It's kind of not making up its mind.
Oh, so if it goes.
Double-minded woman. Anyway, double-minded, that's actually, I'm thinking Proverbs, double-minded man. Unstable in all his ways. Works for both. So what does this mean? Denny's. Breakfast? Anyway. Divergent. Do we find the sum? And the answer is no. How come? Because the sum does not exist. Alright, cool kids. With that, there's one more type you might have gotten confused on. Do you guys have a repeating decimal one? Yeah. Let's talk about this real fast. And we still have time to start 9-5. As iron sharpens iron. The less I have to say, the better. Okay, so this doesn't look at all like the problems we were just doing. Shh. I can say that. Shh. Come back. This doesn't look at all like the problems we've been doing. Does it? Now, real quick, I actually think that the little line is supposed to go over the 1 and the 8, if I'm not mistaken. Does anybody have something to back me up on that?
Yes.
I think it's the 1 and 8. Is it in the book? We'll just say the 1 and the 8 both have the repeating. So that means we have 3.3, 1, 8, 1, 8, 1, 8, 1, 8. How are you supposed to figure out what the fraction is for this decimal? Magically know it. Start doing little like long divisions in your head. 6/7, does that work? No. Instead, why don't we think about this as 0.3 plus 18 over, question, what decimal places is 18 in?
1,000.
What decimal places is the next 18?
1,000.
Wouldn't it be 2 places over?
100,000.
Right? So it'd be 2 decimal places. Couldn't we separate it and say, hey, it's just 0.3 plus or 3/10 plus this infinite sum? And isn't this infinite sum just a geometric series? What's my R in this?
3.3.
No, 0.3 is his own little dude out here.
9 over 500.
1,000.
It's 1 over, not 1,000.
Oh.
Isn't it 100 because it's 2 decimal places?
Oh, right.
Does that make sense? What got added? 2 more zeros. What's going to get added the next time? 2 more zeros, 2 more zeros, 2 more zeros. So my R is equal to 1 over 100. My question, is this convergent?
Yes.
Yeah, R is tiny, right? So if it's convergent, I can say, cool, my decimal is going to be 0.3 plus, can't I plug in my little S of n formula? No, my S formula for the infinite sum. And couldn't I say a sub 1 of, now guys, I'm just looking at this geometric series. The 0.3 I'm kind of just leaving on the outside and he's his own little thing. My a sub 1 would be 18 over 1,000, right? Isn't that my first term? Times. And then wouldn't I have 1 over 1 minus 1 over 100?
Yeah.
So you guys need to see. That's a sub 1 times 1 over 1 minus r. Does that make sense? That's all I'm doing. How would we simplify that? Hold on. Who's 1?
1.
In terms of hundreds, so we could kind of go ahead and put those together.
100 over 100.
Yeah, so we have 100 over 100 minus 1 over 100. What do I have left? 99 over 100. So I have 0.3 plus 18 over 1,000 times 1 over 99 over 100. Wait, 1 over, don't you just flip it? So wouldn't that be 100 over 99? So then, wait a minute, 100 and 1,000, what's left over when I reduce those ones?
1 and 10.
Yeah, isn't it just 1 and 10? There's one more 0. Wait, 18 and 99, doesn't 3 go into that? Oh wait, 3 still goes into 6 and 33, huh? I should have chosen something better. So yeah, 2 and 11. Oh my goodness, 2 and 10. Can I keep going? 2 and 10 is 1 and 5. So now I have 3 tenths plus 1/55. It's not super pretty.
Stick it to that.
Add it in your calculator and then use the fraction button to go ahead and
Stick it to
get all the way through. We could say, yay, we're done, I guess.
22.
But, Caleb, we're going to use your quick knowledge. We could have also done a common denominator, but most of you were like, yeah, no, not feeling it. It actually wouldn't have been too bad. You could have just gotten to be times 2. Couldn't you have just gone to 1/10? Multiply top and bottom by 2, and then 10 goes into 1/10 11 times, so I have 33 over 11 times. Is that true?
Yeah.
11 tens would be 1/10. So is it 35 over 1/10? Anyway. Oh, you can keep going? Oh yeah, because 5 goes into both. Thanks, guys. I heard you guys talking and I didn't realize. Yeah, 5 goes into the top 7 times and 5 goes in the bottom 20 times. So do you think you guys would have kept going to find 7 over 22 in your guesses? Probably not.
Nope.
But anyway, we got it with the infinite geometric sequence. There's your homework. We're going to check it tomorrow. For right now, though, let's get to 9.5. 9.5 kind of has something to do with this guy up here.
Hey, that thing is
Oh,
that's in
square.
But this is called Sierpinski's triangle.
No.
Within Sierpinski's triangle, actually I should say, Sierpinski's triangle can show up in Pascal's triangle. Or does show up in
Wait,
Pascal's.
what's Pascal's triangle?
It's the
We'll see it. Hold on. Wait. Shh. Don't get it. We're not allowed to forget. We're just going to see it. We're going to remind you that way. How? In Algebra 1, would you have to answer these questions? At the top.
Oh.
Wait, shh, shh. You're giving it away? Stop.
Alright,
Told me to.
Okay, pause. How would you have done this in Algebra 1? How do you do a plus b to the 1?
A plus B.
Yeah. Wait. Can I add one? We need to add one. Let's do a plus b to the 0. Okay. What's a plus b to the 0?
1.
Yep. Good job. What's a plus b? Wait, just 1? Yeah, just 1. What's a plus b to the 1? What's a plus b squared? Oh, what do you have to do? Foiling. Can't kill a puppy.
Plus 2B plus.
And we'd end up with an a squared, then plus an ab, and plus an ab, and plus a b squared. I said Algebra 1. A squared plus 2ab plus b squared. Oh, okay. So a squared plus 2ab plus b squared.
Louder.
Kind of, but a little bit off.
Oh,
Scotch. Same opposite, always positive? That's not the one you want. That's for
That's
factoring.
squared.
No, he's thinking about a cubic, and he's right. SOAP is same, opposite, always positive, but not in this case. You're thinking difference of cubes, I think. A cubed minus b cubed. I think that's what you're thinking of, Nathan. How would you have to have in Algebra 1 cubed a plus b?
A cubed plus 3AB plus.
You are not in Algebra 1 in your answers right now.
Oh.
You would have had to go ahead and
weird formula.
do polynomial multiplication. Yay!
That's true.
But some of you are like, ew. And then you like this idea of people saying there's some sort of shortcut to help you out. And there is some sort of shortcut to help you out. And there's also a shortcut for the next one, without having to do any multiplications.
Can I say it or no?
Not yet.
It's Pascal's.
So I'm going to use it in a second. Caleb, go ahead. What do you see?
Oh, wait, wasn't it just. Wait, never mind. I did it wrong.
What are the coefficients?
They're additions of the two above it or whatever.
Doesn't 1 and 1 make 2? Doesn't 1 and 2 make 3? And 2 and 1 make 3? Doesn't 1 and 3 make 4? And 3 and 3 make 6? And 3 and 1 make 4?
Yes.
Yeah.
Pascal's.
Oh.
And what patterns do you guys see about the powers?
They're all
They add.
decreasing A and increasing B. Like as it goes.
The powers do the same thing.
That's what I said.
Oh, no, they don't. Wait. Yeah, they do. Wait. Oh. What? Okay.
Look at it. What's A doing every single time? He starts at the top, and how does he count? Down. And then all of a sudden, oh, he's gone. He's a 0.
Oh.
Starts at the top and he counts down, and he counts down, and then he's gone, A to the 0. Right? As A counts down, what does B do? B counts up. He's not there, and all of a sudden he appears. So he goes from 0 to 1 and then to 2, right? Or from 0 and then to, well, he's not there, but 1 and then to 2 and then to 3. Or from 0 to 1 to 2 to 3 to 4. Now, with all these patterns, even though Pascal's is really cool, and even though we're going to talk about them, if I ask you for some sort of term, let's say the x to the 8th power term of 3x plus 2y to the 40th power, do you really want to make Pascal's triangle down to the 41st row?
It'll be intense.
But it
I believe.
And then we can use it for the next problem.
P.S. Write the binomial theorem, which lets us jump to a particular place in Pascal's triangle without actually having to get there on our own. Go ahead and write down binomial theorem. It allows us to jump to a place in Pascal's triangle without actually having to make it on our own. Yes, this is Pascal's to the 50th row. I'm not sure you'd want to go to the 40th row.
Oh, that's fun. We could do that.
I
Read
believe.
off the 40th row, though.
Dude, wait, yeah, read off.
140, 782, 9,909, 91,560,
Whoa, slow down,
658,498, 3,500,680.
I was gonna do it. Oh.
High school extra credit project.
Really?
How much extra credit was that?
I
It's
wish
not-
I had typed it, but even then that would have gotten messy.
But it
Numbers
doesn't
get really
take
big
that
really
long.
fast, and so then the symmetry's kind of awkward. It's really
What was
sad.
that? That was your high school extra
I should have used scientific notation. Anyway,
Wait, that was yours? Your
Maybe.
high school extra credit thing?
maybe sort of, kind of.
Whoa,
How much extra
you're
credit
so
did you
I don't
cool.
remember. I was just having fun doing Pascal.
But why do you have it? Why doesn't the teacher have it?
She gave it back after she checked it.
Did she check it? Well, was she like, this looks
Caleb,
good here.
stop talking.
Let's see. In honors, we checked the 10th row, and then we checked the 20th row. We didn't check my final row. I was kind of thinking I might have gotten off by then, so then I just kind of
It's so good that nobody.
She said
nobody
whoever
found
could do
out.
it to the highest, like the farthest, would get extra credit. So it was like a
Did you?
I'm
Did
guessing
you
you
do
went
it?
farthest, right?
I'm not sure if anyone else really tried it, but
That's
Can we-
true.
can we
Yeah,
do that?
most people don't.
maybe. We'll see.
Let's see.
Do you guys see this middle thing right here? Even though the pattern is great, and even though the pattern from either end is great, the one that we're most worried about is the center. Because the center allows us, not that that's the very center term, but it's the general term, the center allows us to jump to one place in the binomial theorem without having to do one of those. But the key to the center is NCR, which in probability relates to combinations, which we're not talking about until the end of chapter 9 after our test on the beginning portion. But NCR relates to, this little part right here relates to NCR. There is another notation for NCR that is actually also quite useful. But we're going to come back to this binomial theorem quite a few times because once again, it allows us to jump to a place in a binomial expansion. And technically we could say, let's see, this is the R plus first term. It's the formula for the R plus first term. It's kind of complicated, but if you think about y not being there in the beginning, so y is to the 0 power, then to the 1 power, then to the R power. This is the first term, and R is 0. This is the R plus first term. Okay, if we were to
Looks like a mess.
Find
Oh
the fifth degree of a term, aka a to the fifth power term, if that helps a little bit better. So this whole notation could just be a to the fifth power. This is kind of what I just showed you a second ago. To answer this question, do we want to do Pascal's to the 20th power? And the answer is no. Do we want to do this multiplication? Definitely no. Do we want to be able to jump there with a nice formula? Yes. And we'll work up to being able to answer a question like this. You guys did already start writing it down. Finish writing it down and then skip. I think we only need 2 lines as opposed to 21 rows of Pascal's and then plugging in and chugging. We'll come back to this example when we are able to do so. A couple more seconds if you're trying to get it down, but then skip 2 lines and say, it's a work in progress. We'll work up to it. But first, let's play with NCR. Each of these, whether it has an actual C and a number before, number after, fitting the NCR pattern, or whether it has the N over R in parentheses notation, means the exact same thing. You don't have to write the formula, you guys should have it above in your notes, but NCR, which is the same thing as N over R, is bound by N factorial all over N minus R factorial times R factorial. N factorial over N minus R factorial times R factorial.
28.
Sometimes using your calculator is definitely an option. Sometimes it is not. So we're going to do a few of them by hand. But yes, this is also a button in your calculator right above where you guys have been finding factorials. But once again, sometimes using your calculator is an option and sometimes it's not. So, how would we set up just plugging and chugging 8 choose 2? 8C2. On top, 8 factorial. On bottom, how's the formula go? N minus R factorial times R factorial, which ends up with 8 factorial all over 6 factorial times 2 factorial. Now, kiddos, how am I able to say that's 28? Okay, that was faster than a lot of you guys in your calculator. But Nathan, what did I do? Can you tell? Remember how we can do factorials, kiddos? We can count 8 down until it meets with 6, and then we can say, cool, 2 and 8, doesn't that reduce to be 1 and 4? And what's 4 times 7? 28. In section 9.5, you guys are able to start doing your NCRs, but I would probably stop when it gets to expanding. And definitely stop when it starts saying jump ahead. Alright, cool kids, finish 9.3 for tomorrow. If you got a little stuck on it tonight,
Do you know when we're
start section 9.5.
Hey, Miss D, could I have extra credit if I do
At this
40
point, we're kind
rows
of
of
barreling
Pascal?
to Tuesday, so you'll probably get it back Tuesday.
How many rows?
Maybe after you put in your test. Maybe. Bye, guys.
Miss D, can I get extra credit if I do 40 rows of Pascal's triangles?
40 rows.
Yeah, just like you did.